chirality. This is needed before going into the other stereoisomers known as configurational isomers. So for chirality, a molecule can be considered chiral if the mirror image can't be superimposed on the original molecule. So this means the molecule lacks a internal plane of symmetry. So if you cut a molecule in half and it's symmetrical, then it would be considered chiral. And this is important because this determines what kind of, how many different kinds of configured isomers a molecule can have. And if a molecule is chiral, it can interact with and polarize light. So we can say for a molecule that's chiral, it can have optical activity. And a molecule is considered achiral if it can be superimposed on the mirror image. So if a molecule only has 3 different substituents on a carbon, then the carbon is considered not a stereogenic center. So a stereogenic center, otherwise known as a chiral center, this is a carbon that has 4 different substituents attached to it. It is asymmetrical and the core of the optical activity. So because of this chiral center, it can give a molecule optical activity and polarize light. And this is, like I said before, it's only considered a chiral center if it lacks a plane of symmetry. So if you see the figure on the right, the ones with a chiral center, they have 4 different substituents bonded to it. So for this left chiral center, you can see that it has 3 different chains attached to it, and then you can assume there's a 4th bond to a hydrogen. So all those 4 substituents, they're all different. Same thing for the chiral center in the middle. It's bonded to 2 carbon chains, a hydrogen, and then this chlorine molecule. So since these are all 4 different substituents, it can be considered a chiral center. But then this arrow on the right, it's pointing to a carbon that's not a chiral center because it's bonded to 3 carbon chains, but 2 of them are methyl groups, which are the same group, and then a hydrogen group. So it would only have 3 different substituents, which wouldn't make it a chiral center because it needs 4 different groups. So any molecule with at least 1 chiral center can be considered chiral if it also doesn't have a plane of symmetry. So to figure out the absolute configuration of a chiral center, you have to assign a priority to the 4 substituents. So those are the 4 different groups attached to the chiral center, and you have to do this for all the chiral stereogenic centers. So when considering priority, you assign the atom connected to the carbon with the highest atomic number with the highest priority. So usually the bigger molecules attached directly to the chiral center will be given higher priority. So you assign it the highest priority. So usually I signify that as 1. So I would give 1 to the atom with the highest atomic number. But if they're, let's say, both attached to carbon, if there's 2 groups with carbons directly attached to the chiral center, then you can determine the priority by the other molecules attached to it. So look at the next molecule. If they're both attached directly to a carbon from the chiral center, then look at the the other group attached to a carbon. So if one carbon has another carbon attached to it, while the other one has a nitrogen attached to it, then the one with the higher atomic number attached directly to that carbon has the higher priority. So when they have the same priority, then you move the same atomic number, then priority is determined by the rest of the atoms attached directly to that substituent. And for double bonds, you have to count them as 2 individual bonds, and then triple bonds, you have to count them as 3 individual bonds. So if it's a carbon is double bonded to another carbon, then you have to count that as 2 single bonds to a carbon. And for triple bonds, same thing. If a carbon is triple bonded to another carbon, then you have to count that as 3 single bonds to a carbon when counting priority. And likewise, if it's still a tie, to determine the priority, you have to keep working outwards from the stereo center. So consider the other molecules attached to that carbon. So usually what I do is I have the lowest priority group in the back while the other 3 substituents radiate out of the page. So I would give the 3 higher priority substituents either a solid line, or you can use a wedge line to signify that they're not pointing towards the back, pointing either along the page or out of the page. And then the lowest priority functional group, you can have that as a dashed line to show that it's pointing into the page because it has the lowest priority. Usually it's like a hydrogen group. Those usually have the lowest priority. So it's usually a hydrogen group sticking into the page. And then, so to show the absolute configuration of the chiral center, you draw a circle connecting the substituents from highest priority to the next priority group. So you would go from 1 to 2 to 3, and then the 4th priority group, which is the lowest one, would be the ones sticking into the page, so you don't count that when drawing the circle. And this is to determine if it's an R or S configuration for that chiral center. So for S, it's an S configuration if the circle that you draw is a counterclockwise circle, and then an R configuration if it's a clockwise circle. So in this diagram below, you can see that the highest priority group is on the bottom left side. The second highest is pointing up, and then the third highest is pointing to the right. So when you draw a circle, you connect 1 to 2 to 3, and that shows a clockwise circle. So that would be R configuration. And then for S configuration, it would be opposite. So starting from 1, if you draw a circle from 1 to 2 to 3, this one on the right, you can see the circle goes counterclockwise. So that's an S configuration. So usually I remember this by how I write an R and S. So when you begin writing an R, when you begin writing like that half circle in the R, you go clockwise. So this is how I think of it. So when you draw an R, you go like this, right? So you're going clockwise when drawing an R. And then for S, when you start to write an S, you go counterclockwise. So when you have to determine if it's R or S, when you have the functional groups, try to remember how you write an R or an S and which direction that goes. And that will help you determine if it's R or S, depending on if the circle is clockwise or counterclockwise. So for S, the circle has to be counterclockwise, and then for R, it has to be clockwise. So after you determine the priority of the functional groups, have the lowest one sticking into the back, so don't consider that when drawing a circle. And then when you draw the circle from highest to second highest, third highest. If it's a clockwise circle, it's an R configuration, and then if it's a counterclockwise circle, it's a clockwise counterclockwise circle, it's a S formation. Let me get rid of this.